So guys, here's your friendly lecturer Jerry back again with the review lecture that I promised you. It's just a summary of what you've done so far with Abdel, and it's as I say, it's not meant to be a critique of what he's done. Believe me, it's more for me more than for you because I just want us to have a kind of common grammar, a common base from which to work. Okay, so I'm going to be using different functions and maybe doing things in a slightly different way to the way that Abdel has done it, and so therefore you might kind of want to get me or get into the way I start thinking about databases. First thing I want to talk about is that I just want to talk about a little bit about database management. Database management is kind of the high level or is the first thing before you do any data analytics. You need to do some database management. And so it's a kind of a high level part of the course. We're not going to do very, very much with this, actually, database management. It's a whole course in and of itself, guys. But the most basic component, though, of database management is uploading databases into whatever software you're going to use, and we're going to be using R. And I don't know if you've had much experience with this, and we're going to maybe start doing this a little bit more. It's problematic. Unbelievably, it's problematic because it's something that should be very, very simple. But the problem with databases is that they're stored and they're in different ways by different people, and there's no common standard or no common database structure that's out there. So it is problematic to get data uploaded into R. And it's the most basic problem, because if you can't get your database into R, you can't do any data analytics. So I want to spend a little bit of time on this, not too much. And we're going to look at very, very simple uploading. We're going to concentrate on what's called CSV files. But there are loads of other different files as well that you can use that are out there. But we're not going to have time to look at them. But it's basically the same idea in each case. The second part of database management is database cleaning, which is really, really important. Sometimes if you have a database, there's missing values. And R doesn't like missing values, especially when it starts calculating quantities for you. Typically, you need to have a column that's clean of NA values or missing values in R. And Abdel, I think, has talked about this, about how important database cleaning is and how you do it. So we're not going to spend much time on this at all. The third part, which is not what we're going to do, we're not going to touch this either, is called database merging. And when we start looking at databases that are out there on the web, you will see that in many cases the data is spread over a number of files. And what you need to do is you need to merge those files into a single database. Now that, as you can imagine, is a course in and of itself, and we're not going to look at that at all. But just be aware of it. And as we'll see it in a second when we start going onto the web, looking at databases, that it's quite common, and it's a very, very important part of data analytics. But again, due to time constraints, we're not going to be able to do it. Okay, so let's look at a database, and as you've seen some examples of this before. So a database basically is just data stored in columns and rows. So if you've got columns and rows with data in it, you have a database. And what can be in the columns and rows? I suppose the most basic quantity in a database is the column. And the columns are sometimes called variables. And the variables can be either numerical, which is the kind of the focus of engineering, but also categorical. And categorical are labels associated with the numerical quantities in numerical variables in databases. And basically they tell you what the number is, or what category the number belongs to. Now, I'm making this sound very, very esoteric and very confusing. It's not that confusing, really. Maybe an example would be if you have numerical data on blood pressure, the categorical variable beside it would be maybe sex, whether the patient was male or female. So that's what, and so the male or female would be a categorical variable. The blood pressure measurement would be the numerical data. Okay. The rows are typically just numbered elements of the columns, and they're not as crucial and not as elemental as the columns. So they're just numbered elements of the columns usually. And as I said to you before, as just in the previous slide, the crucial first step is getting data into R. And when I first started messing about with this stuff, I couldn't believe how hard this step here is, because databases have many different formats online. And when you start trying to import them into R, sometimes you don't get all the data, and it's just very, very, very messy. And it's just one of these things you just have to play around with until you get what you want. Okay, so but that's the crucial first step, being able to do this. And as a result, then what's called the read.csv function is probably the most important function in R, because it doesn't do any data analytics. All it does, it takes data in CSV, comma, separated variables format, and it reads it into R, into a portion of memory that R can use. And so therefore, this is the most important function in R, because without the read.csv function, you can't do anything. And I'm going to do this an example in a minute, folks, about this, and I just want to show you. But what's very, very confusing as well when you begin this is that R only can read data from the working directory that it's in. So you must store all the databases that you're interested in your working directory. So what you do is you come up, you go, before you do any data analytics at all, you set up a folder, maybe called databases. And then what you're going to do is you can put all your databases into that folder. But then you must tell R where that folder is. And to do that, then you use what's called the MISC tab in R to actually tell R where to go. And we'll do an example in a minute, folks, so don't relax. I'm going to go through the slides now, and then I'm going to use R and show you what's what here. Okay? Now, so we haven't done any data analytics yet. We've done, the read.csv function, kind of database management more than data analytics. But what we're going to do now, guys, is the most basic part of data analytics. And you need to understand that this is the most important part. Data analytics is this huge field, and everybody knows, it's machine learning and all these very sophisticated, supposedly, ostensibly sophisticated concepts. But the most crucial concepts, guys, are what are called summary statistics. Okay, now there are two types of databases, guys, and there's ones with just numbers, which is what we're going to be looking at initially, but there are also ones with numbers and categorical variables. Remember, I talked about categorical variables. Categorical variables are columns with labels. So we're going to focus initially on just pure data and looking at summarizing the columns of pure data. And in the next lecture, we might start looking at databases with categorical variables as well, and show you how much more difficult analyzing that data is. Now, if you don't have categorical variables, so you open up your database and you just see all numbers, you're laughing. Because then what you can do is you can treat each column as a single basic unit in your database. Once you have categorical variables, then most of the time, the categorical variables mean that you must subset your columns into distinct parts. Don't worry about it. We're going to just look at just databases with just pure numbers at the beginning. Now, here's the most important part of in my view, of what data analytics is all about. So the most important part of data analytics, summarizing data in a column. Now, you need to remember this, folks, because there are 4 things you need to be able to do. So if you've got a column of numbers, no matter how big the column is, there are 4 things you need to calculate. The first is what's called the mean number, which is just a typical number. And you've seen this already from maybe national school, even going back to national school. But the mean number is by far, well, it is an important, I won't say it's the most important statistic, but it is an important statistic. But the mean is just a typical number. So if you have a column of numbers, no matter how big, once you calculate the mean, that tells you what a typical number in the database is. So so essentially what you can do is you can replace, say the column is 6 million entries, you could replace each of those 6 million entries with the mean value, and you still have essentially the same column. So that's why it's important. The second summary statistic that you need to be able to calculate is what's called the standard deviation. And this tells you how spread out the data is from the mean value. So it's a measure of data spread. And actually, remember I kind of stumbled initially over the mean value there. The standard deviation probably is more important than the mean in engineering, actually, because the standard deviation measures consistency and variation in the data. And it's maybe not obvious to you, but variation in the data is what's interesting, is what makes the data interesting. If you have a column of numbers which is all the same number, it's not very interesting. It's the variation is what makes the data interesting. So standard deviation measures variation or consistency, and therefore it's probably the most important summary measure that you can do. The third measure that you need to be able to calculate is what's called the median. And the median is just the middle number. And most of the time, the median is almost the same as the mean. And they're almost identical. Okay, so you can think of the median as it is the middle number. That's what it is by definition. But it also gives you the typical number. There are some situations where the mean and the median are different. And in that situation, you have what are called outliers. And I talk about those in a minute. And the fourth thing that you need to be able to calculate, folks, is the frequency plot. And this is your first introduction or your first example of visualization in data analytics. And that's an incredibly important tool, an important concept, an important component of data analytics is data visualization. And this is probably your first exposure to it. And it basically tells you how the numbers stack up. Yeah, where they are, how many of certain types there are, and it is a very, very important plot to have. So you've got, and so you need to be, if you've got a database of just numbers, for each column, you need to be able to calculate in or each of those four quantities. Okay, that's the basic test, folks. So hopefully you do know how to do that. Okay, and if you don't, you better learn it, because this is what you're going to be asked to do. All right, so each of these four quantities, you need to be calculated for each column of numbers. Okay. Now, the calculation of the mean, median, standard deviation, and the frequency plot, you can do it for each individual column if you like, but I'm going to show you some examples of where maybe you might do it all together. You do for all variables at the same time. It's much more elegant, and it's much more efficient, and it's much more impressive, and people are wowed by this. They're not so much wowed, by calculation for individual columns, but when you put all the columns together and, you do the same you just single line of code for a database with maybe 600 columns, then it obviously becomes a lot better to do this collectively. Get all these four quantities collectively using a single command. I want to talk about that. Now, the last thing you've probably been doing, I think that this is what you've been doing with Abdal, is a thing called confidence intervals. And this is a kind of a sophisticated addition to these four quantities. And you can do it. I suspect that when you are working as engineers, just calculating the mean, median, standard deviation, and frequency plot would be impressive enough. But if you want to go if you want to be the blue-eyed boy stroke girl, you might want to look at calculation of confidence intervals as well for the mean. So we're going to be looking at maybe confidence intervals for the mean for each of the columns. Just for the mean. You can also do it for the standard deviation, but it's a little bit more sophisticated, and we don't have time. So that's a standard get out for me for this course. Oh yeah, we can do it, but we can't because we don't have the time, especially this semester for obvious reasons. Okay, so just don't forget what a confidence interval is. It basically gives you a range of numbers within which you're pretty sure the mean value lies. Now, if you're not into confidence intervals, don't worry about it, because just calculating the mean usually is enough. That gives you that gives you so much information about what's in the data set. Okay, outliers. I talked about outliers, folks, and there's a little picture there at the bottom, and I kind of like this one because it kind of reminds me of me. Like I'm the white bottle there in mechanical engineering. All the other lecturers are super cool, and I'm not. I'm just the white bottle, and they're all sophisticated black bottles there. Maybe you can identify with that white bottle yourselves. Okay, so that's, if you look at the picture there, the white bottle is the outlier. It's one of these kind of Sesame Street things, actually. One of these things is not like the others. One of these things just doesn't belong. And maybe that speaks to you in many ways. Okay? But outliers and statistics are incredibly important. And if you get into this game at all, identifying outliers makes you a superstar in the data analytics world, because outliers sometimes have a lot of information. Okay? So, an outlier is a data point that differs significantly from the other ones. Okay, think of the Sesame Street thing. One of these things is not like the others. So usually what happens is you have a list of numbers, folks, and you've got one number which is self-evidently different from the other ones. It's like, you've got ones and zeros, and then at the end you've got 6, 9, 5, 4, 3. And so it's kind of obviously that there's a problem there. There are two classes of outliers. One which is called the extreme values, which are the interesting ones, and two mistakes. Sometimes there's an outlier there because somebody's input the data incorrectly. But even identifying that is good, because you can then make sure that no mistakes are made again, or similar mistakes aren't made again. The first case, the extreme values, are more interesting because they're possible but unlikely, and they are worth investigating in and of themselves. Why did this outlier occur? And that idea of extreme values, or outliers, is the basis of statistical quality control. The idea in SQC, statistical quality control, is that if you have an extreme value, if you have an outlier, you should stop the process and investigate what caused the outlier. And this is the reason why Japanese industry, just that basic idea, is so efficient, because they firmly believe in that as a principle. And it's a very, very good way of approaching engineering systems, and maybe even life itself. Who knows? I don't know anymore. Now, guys, here's what's very, very important. Sometimes I look at student projects, and sometimes they calculate the mean and the median. And a very simple way of identifying outliers is if the mean value and the median value are different. If they're significantly different, if those two things are different, are significantly different, if one is much larger than the other, then you know you have outliers. And you get the mean and median most easily together from a database by using what's called the summary function. And we're going to be talking about that now in OR. So the summary function is really, really important. And we're going to use that now too. I'm just going to just talk about a little bit about that now, and how you use it in identifying outliers. Okay, so that's the end of this, of the little talk here. Now I just want to do a little bit in OR itself. So I'm going to come out of this. I'm going to go into OR. All right. Now, I was going to do just upload a database, folks, and do some simple calculations and some simple manipulations for you, and then we'll leave it there. Okay. So what I want to do now is I want to show you. There are two types of databases. There's some databases built into OR, which are very, very useful. I'm going to use them a lot, actually, because they're nice and clean. Somebody has gone to the trouble of identifying databases that are useful for explanation of OR concepts, but they're not very interesting. It makes much. I think makes much more sense to go online and have a look at databases there. There are two main. There's loads of different database repositories, places where you get data from, folks. You can go to, like in Ireland, you can go to the CSO, the Central Statistics Office. They have a shitload of data that you can use. I'm going to edit the word, the S word there, in a minute. Or any, the World Health Organization, United Nations, the European Union, the Eurostat have, just an incredible amount of data that you can play around with. But typically there's a number of websites online that are well known as being good sources of databases. The most topical one at the moment is 538, which is a very, very well-known website in the States. It's based in the States. It's a data analytics website for politics and sport. It's run by a guy called Nate Silver, who is a data analytics genius, god. Everyone looks up to this guy, super cool. So that's worthwhile looking at. So it's called 538.com. It's very, very interesting, and they do some very, very interesting data analytics analysis for free. They just put it up there and they just take a problem and they do it. So that's for me, that's a really, really interesting thing in what they do. But there's other websites as well. One of the websites, let me just show you here, is what's called the UCI database repository. And the UCI database repository, folks, has enough. It's probably it's the one that academics probably most use. Okay, UC is University of California at Irvine. So therefore, there's an awful lot of data sets there. Very, very useful. Some very, very appropriate for engineering as well. One of the problems that I've noticed about this, and this just as an aside, is that they've gone away from actually using CSV files on the UCI database repository, and they've got into more using .data files. So they've got a name, .data is the file type, and although .data can be read using the read.csv function in R, sometimes, most of the time you can't do it, and you have to do arsing around. So this kind of puts me off a little bit from the UCI, and this has only happened in the last couple of months. Actually, they've kind of transitioned from CSV files to data files, so .data files, and it makes reading into OR a little bit more tricky. But you can see, look, the folks, there's an awful lot of data sets here, and you can just download them there. If you go up here, these are the most popular ones here. The adult one here is not what you think it is. You're going to be very disappointed when you go in there, and you won't ever want to go back again. But you can actually go through this, and it's a very, very well-known database repository. The one that probably is more appropriate for us, and it's much more kind of hip as well, is what's called Kaggle.com, Kaggle.com. And my claim to fame is that I've been banned from Kaggle for some reason. They rescinded my registration. Don't know why, but maybe they recognize, I don't know, some hacker quality in me. But I think I'm back in again. So if you go to go in here, we're going to use maybe the Kaggle data site a little bit more than the UCI one, because Kaggle usually stores the data in CSV files, in a nice clean CSV files, which is good for us. Okay, so if you look at the Kaggle site, folks, actually, just as we're here, this is a great site because there's a lot of competitions on this. They run competitions. They give a database problem, or they give a data analytics problem, and they want people to solve the data analytics problems. And if any of you are interested in finding your project in this area, go into Kaggle here and have a look and see what they're interested in, and maybe contribute, maybe submit an entry into a competition, because it'd be good. This is a great area to be in. Data analytics, especially as an engineer, the intersection of data analytics and engineering, I think, is going to become much more important in the future. And to have any background in this at all would be very, very helpful. But again, it depends on luck, of course. Okay. Now, if you go into the data section, you see all the public databases, and there's a lot of them, folks. Okay, so there's a lot of databases there. Now, what's surprising actually is that when you start looking at these databases, how few numerical databases there are. Most of the databases that you will see here are categorical databases. So they have columns of yes, no, male, female, Trump, Biden kind of thing, and so from an engineering perspective, very kind of uninteresting actually, and it's very difficult to find databases with just pure numbers in them. But let me just come down here. I think the mushroom classification, folks, I went in there, and it says what it says in the tin. They classify mushrooms. It's not good. It's a waste of 5 minutes of your life. But what one I came across here is, it's way down here. Now it's, keep going. It's a Wisconsin breast cancer data set. Now, apologies if this causes if this is a sensitive topic for people, but it's a nice data set because it's nice and clean. So if I go in here, if I go and look at it, it's a CSV file, and I'm going to download it, and it's only 122 kilobytes, so it's very small. So I'm going to download that, and then what I'm going to do, folks, is, now this is what I'm at the beginning of the lecture I talked about making sure that the database that you're interested in is in your working directory. Now I have a file, I have a folder called databases, and I'm going to put this data into that database folder. Okay, so make sure you do this when you're working in data analytics. Have a folder where you put your databases and work with that folder only. So if I go down here to downloads, I see that this data here is called data.csv. Very badly named, and we need to change the name actually, because that's data.csv is too generic. But let's just take this. I'm going to copy that, and I'm going to go into my database folder. Okay, and guys, because that's a terrible name, you know. Let me just say MM382 cancer. Okay, so we know what it is. Okay, so okay. So I've put this into the database, and we're going to have a look at it now. Okay, so I go into R. Now, as I said to you at the beginning, folks, oh yeah, I'm going to just by introduction, I'm just going to use base R, guys, pretty much all the time. Now, I know that you've been using RStudio with Abdal, and if you want to continue working in RStudio, off you go. But for me, because the screen is nice and big here in base R, I'm going to use base R. So it's a little bit easier for teaching, actually, just to use the base R. But there's a lot of functionality in RStudio which you might prefer. And if you're happy working in RStudio, stick with it. If you ever get into this game, this data analytics, and want to do this professionally, you will be working in RStudio all the time. Okay, because the database management section of it is very, very good, and the plotting section is very, very good. It's not as good in base R. The most important folder, folks, here in the base R is the MISC folder, because it tells you about the working directories, or how to change the working directory, how to reset, and how to get the working directory. Now, if I click on get the working directory, it tells me that my working directory is the database folder into which I put the MM382 cancer data base. Okay, so I'm good to go. If your data is in another folder, you need to go up to MISC and change the working directory and tell or where to go to read the data. Now, when you first start off, folks, this is a very, very easy step to forget. And you can go in there and you start reading, read.csv, everything, and you're saying, oh, it's not loading up, oh, stupid or. It's not stupid, you just haven't put the data into the working directory. So do it at the beginning. All right. So when you're in R, when you first open it and you first want to start looking at what's there, the best thing to do, guys, is just make sure that your database is there. I've got MM382. I can't see it. Is it there? There it is. Okay. So that's my data file here. So I'm going to copy that, folks. I'm going to read it into R. But you always, when you read a database into R, call where you're putting the data a name that you can use. Okay, so call the section of memory that you're putting the data into something. So let me just say CD. Okay, cancer data, and I'm going to do read.csv. Open the brackets, and then this. Now, be very careful with the quotes. R is very particular about these bloody quotes, and they cause untold frustration. Sometimes they want single quotes, sometimes they want double quotes, sometimes they don't want any quotes at all. But certainly, when you're using the read.csv function, folks, you need to have the quotes in, and if you don't have the quotes in, it won't work. Okay, so I've done that. Once you've read the data in, it's always essential, a first step before you do any data analytics at all, is just to interrogate the database and see what's in there. Just get a general idea of what's in there. So the first thing I always do is I just get the dimensions of the database. So it's using the dim function. And in this case, I see there's 569 rows and 33 columns. All right, that's cool. And the next thing I do then is I know that so it's not a very big database. Okay, a lot of columns, but not very many rows. Okay, so this is not a very big database at all. The next thing I use then, folks, is I use the structure command. Sorry. To see what's in OR. The structure command is very, very useful. Okay, so the dim is the first one I use just to get the idea of what's in there. Then I use the structure command on the database, and I see what I get here is a data frame. Now, what's very important, folks, is that when you use the read.cs function, the read.csv function stores the output as a data frame. And a data frame is the most basic data structure in R. And it's the simplest to use. It's very, very, very convenient. There are many other types of data structures in R, things called like tables, matrices, time series, which I'll talk about later on. So there are very, very many other databases structures, but the data frame is the most important one. And you see here, guys, look, there's numerical data, and there are things called factors as well, and integers as well. So, but the factor is a categorical variable. There's two levels, B and M, whatever they are. Okay. So it's the numerical data that's what we're interested in. Okay. Now, if you want to get, as I said to you guys, the very, very important thing is that you need to be, so if you look at all these numerical variables, all right, the radius mean, the texture mean, the perimeter mean, down to the fractal dimension worst mean, or worst variable, they're all numerical data. You need to be able to calculate the mean, the median, the standard deviation, and the frequency plot for each of these guys. Okay, so let's see how you do it. Now you can take individual columns and do that, but by far the simplest way to do this is use the summary function, and the summary function gives you these 6 quantities for each of the numerical columns. It gives you the min value, the max value, the first quartile, the third quartile, the mean, and the median. Okay, the first quartile is the value below which 25% lie of the data values lie, and the third quartile is the value above which 25% of the data values lie. Okay, the median is the middle number, the mean is the mean. It's the you add up all the values in the column and you divide by the number of values in the column. Okay, now before I forget this, because I will forget this, if you look at some of these columns here, remember what I said about outliers. You know you have an outlier if the mean and the median are significantly different. So if you look at the texture mean column here, look, you see that the median is 18.84, the mean is 19.29. They're pretty much the same, folks. So you don't have any outliers there, which from a data analytics point of view is kind of disappointing, actually. It's where you have outliers is what makes it interesting, or you can become a superstar. Now, if you look at the area mean, though, you see 551,654. They're not very close. You know, there's about 20% difference there. No, is there 20% difference? Yeah, but about 20% difference there. That could be significant, but we're not sure. Okay. If you look at the symmetry SE column, you see it's 0.1 or 0.0. Yeah, that's pretty close as well. Okay. So there are not very many entries here, or columns here, where you have outliers. And you can tell that just by looking at the mean and the median value and comparing. Now, all right, and it's a very, very simple way to do it. Okay, so that's so the summary function gives you the mean and the median for each of the columns, which is cool, but it doesn't give you the standard deviation, and there's no talk about the frequency plot. So you need to be able to do that. Now, one problem with the summary function, folks, is the way the output is the way it outputs the data. So certainly if you wanted the median for the concavity mean, the mean value there, you could just highlight it, as I'm going to do here, and copy that and save it and just use that. That's fine. But it's not very elegant. And if you want to get the mean value for each of these columns here into a single data structure, what do? It's not very elegant. And I'm going to show you a way in a second now how to calculate the mean value for each of these numerical quantities. All right. Now, yeah. So I've talked about outliers. I've showed you how the mean and the median are calculated for each column using the summary function, which is really, really nice. But the basic problem is that we don't have the standard deviation and we don't have the frequency plot. Frequency plots are a bitch to calculate, but we're going to do it here. Okay. So let me talk about the frequency plot first, folks. So the frequency plot is just a plot it's a plot of the frequency of each of the numbers, and it gives you a very good pictorial description of what the data looks like. So let me look at, for example, it doesn't matter which one we look at. Let's look at the compactness worst column. Okay, so I'm going to copy that. So I'm going to, now, I don't know if, I'm sure Abdul has done this, or maybe he hasn't done this for you, but here's how you get the frequency plot. You plot density, CD. So the CD $ compactness worst means you isolate the compactness worst column from the CD database, and you plot its density. Okay, and I'm going to do that here, and this is what I get. Now, most data many sets of data have what's called a normal structure. Now, this isn't a normal distribution because a normal distribution has the bump, this bump here, in the middle. Now, this bump is not in the middle, it's to the side. So this is a skewed data set, but it gives you a very good idea of what's in the data, right? So it gives you a very good idea of what the data looks like. You see there, look, that many values are around 0.2. There's a few very extreme values on here about 1.2, and very few values around here around 0. So it gives you a very, very good idea of what's going on. The density plot, folks, is extremely important. Do not forget to plot this for each of your numerical quantities. Now, I don't know how to do this. It's very difficult to do this because it's very power consuming. How you do this, for instance, for this database, how to get all the frequency plots together. Because I would have to, the only way I know how to do this is I would have to just do what I've done there for each of the columns. And so that's kind of a little bit embarrassing. Maybe there is a fancy way to get them all plotted out together. I'm not sure. Okay, but I suspect the only way, the way that you have to do it is just do what I've done there for each of the columns in your database. I do know a way of actually calculating the standard deviation for each of the columns together as a whole, and that's using what's called the apply function. Now, what you have to do is you have to be a little bit careful. Now, as I said to you before, R is very, very finicky in that it sometimes does what it's supposed to do and sometimes it doesn't. Okay, so if I use the apply function, this gives you I'm going to use CD because that's my database. I'm going to do number 2 because I wanted to do the analysis on the columns, and I'm going to type in SD for the standard deviation because the standard deviation function in OR is SD. So I'm going to oh, sorry guys, that's not good because it should be round brackets, of course, because this is a function. Now, usually when you do this, you get this kind of get this idea, okay? Now, it doesn't like the fact that in the diagnosis column I have NA values, and in the X column I have NA values. But at the moment, though, it's quite happy though to calculate the standard deviation for you. So the standard deviation then for each of the columns is given by the apply function. Now you can do exactly the same thing here. The warning here, guys, is, as I say, you've got NA values in some of the columns, and if you have NA values in columns, the standard deviation or will not calculate the standard deviation for you. So that is a pity. Bizarrely though, if you go back into the summary function, it calculates the mean and the median even if you have NA values. The summary function does that, but the actual apply function won't do it if you have NA values. This was one of the quirks of OR. Okay, but here this is a very, very important idea because you need to be able to calculate the standard deviation for each of the 3 columns, as I've said, because that's a basic idea. It's a basic summary quantity, and this is how you do it. You use the apply function. Now you could do the same thing then, folks, if you wanted to. This is your database. It's the CD database. You want the in this case, I'm going to calculate the mean. I want the mean to be applied to the columns. So the columns in OR in the apply function are denoted by 2. If you want to do the mean values for each of the rows, which you very rarely do, you instead of 2, you have 1. So if I do that, there's a problem with the mean value. So the mean value here, folks, this is where it gets really ridiculous in OR. It doesn't like the fact that you've got NA values in your diagnosis column and in your X column. Okay, but in one sense, it doesn't really matter because you already have the mean and the median from the summary function. But what I find very, very interesting, it's just bizarre, is that if you use the apply function to calculate the standard deviation for the columns, it will do it, even though you've got NA values in some of the columns. But if you use the apply function for the mean, it doesn't do it. And in that case, if you still want to use the apply function to calculate the mean, you have to subset your columns. So you have to get rid of the columns with the NA values. And in this case, what you would do maybe, if you come back up here to your structure function, The first column is just an ID column, so you might not be interested in that. The diagnosis is a factor, which has got NA values. It doesn't like that, and the X column is a non-numerical value as well. It's a logical variable. So you might just want to focus on the numerical columns, and one way to do that in R is to just to get rid of or focus only on the numerical quantities is to have, say, this CD num. And what I'm going to do, I'm going to take my CD column, and I know the first numerical quantity begins at, and I'm going to have a comma. I know, bizarre. At 3, colon, and there's 33 columns here, isn't that right? And I want to exclude the last one, because let me go back up to my, yeah, there's 33 variables. So I want to exclude the last one. So it's 32. I do that. If I do dimension of CD num, exactly what I want. I've got the 30 numerical quantities now, and there's 569 rows. So I think CD num is good. If I now apply the apply function to CD num, I'm in. Okay, and this reproduces what you have in the summary function. And you may not want to do this. That's fine. Okay, but I just want to point out the fact that you can actually use the apply function for the mean and for the median as well if you want to. And if I come back up here, folks, to the frequency plot function, remember I did this way back here. Here, the plot density function, that's a really, really important idea. Being able to see what the frequency and see how the structure of the data, what the structure of the data is between each individual columns. Okay, so I think this is where you are with Abdal, and I'm going to take it from here. Okay, and I might have a little tutorial set on this just to get you used to this. Okay, and get you happy with using different things. You know, the apply function and the plot density function for different data sets, if that's okay. All right, guys, that's it, and I will talk to you soon.